see what is when the exponential function, when the sine function and the cos function, product of sin x and cos x, polynomial function. We will see that examples, 2 or 3 examples, right? Okay, we'll see one by one. So this is the most important, because already we observed in the morning session, dy by dx is equal to f of xy. Here we are observing one derivative y dash and one arbitrary constant the solution gets. Initial conditions we are having. Solutions, solution curve. And we are using that tools, we can use dsolve or ODE. Here also we are having, suppose when it is a second order differential equation, we are having the derivatives y dash and y double dash. By solving that second order differential equations, we are having C1 and C2. Just I am giving the glance of this one. Then we will see that Python programming for each and every example later. Within a short time, we will see every example and how you are going to use Python programming to solve these differential equations, right? So first, detect and order. That is the first building blocks. See here. The most important, this is the first one. Whenever the differential equations we are giving to that Python, then first that program is going to detect what is the order of the differential equation. That is very important. And here it is, we are having detect order, detect underscore order dot py. And we are having show underscore order. So the next building block is to find out whenever the second and higher order differential equation. First, we are going to find out the first part of the differential equation. Second and higher order. The first part is coming from homogeneous of f of d of y is equal to q of x. The homogeneous part we are going to convert, we are into an algebraic expression, which is an algebraic equation to find out the roots. So that polynomial, which is called a characteristic polynomial, right? So if it is a second order, we are getting the second order polynomial, third order polynomial. The third part is we are going to find out the complementary function. We are going to find out the particular integral also when it is a non-homogeneous case. So that function, which is called the forcing function, right? So we are going to see these three in the next coming few minutes by using programming, right? Okay, we'll see one by one. So this is phase one. First one, detect order and given equation. So the step one, where this is the input, we are going to input LHS as y double dash plus y dash plus y. Directly, if we are going to input, that program doesn't understand this one. So we have to learn that input. This is a differential equation. We have to tell that program this is the differential equation, right? So just not like that. It is not the symbols. So that's why we are going to use some methods, right? We will see that one in the programming part. Step one, the next one, find out the order. So for that order, we are using the methods system.ode underscore order. All these all in import SymPy. Next one is a classification, whether it is a homogeneous or not. And coefficients, we are going to take the coefficients of every order, the second order, because we are going to get the characteristic polynomial. For characteristic polynomial, we are going to pick up all the coefficients of the derivatives, right? We are getting the roots. So, and finally we get the solution, right? That is called the output. So we'll see one by one in a programming way. So this is the case for forcing pattern. So we are going to use all these right hand side functions. So we are going to see by using these forcing functions what is the output of that particular program, right? So mostly we are going to concentrate on programming, right? We will see one by one. We'll go to that program. So as all of you know, whenever we are having, again, I am taking 2 minutes of time. So whenever it is a homogeneous differential equation, so the general solution is the complementary solution itself. The complementary solution is obtained from the first, we are going to take the operator form and find out the algebraic equation and find out the roots and the complementary solution depending upon the roots of the characteristic equation, right? So when the roots are equal, then all of you know, then we can convert that second order differential equation into a first order linear differential equation. And suppose then it is d minus, suppose when the roots are 2 and 3, then that algebraic equation can be expressed into as d minus 2 into d minus 3 into y is equal to 0. So if you are taking that d minus 2 into d minus 3, that factors. So that factors itself is a linear differential equation. Suppose if you are taking that d minus 3 of y is equal to 0, that d minus 3 of y is equal to 0 becomes a linear differential equation. Then by solving the differential equation, we get e power 3x is the solution. If you are taking that one factor d minus 2 of y is equal to 0, then it becomes itself a linear differential equation. We are going to get e power 2x. The linear combination is its solution. So therefore, the combined solution is the general solution is nothing but c1 e power 2x and c1 e power 3x. So why you are getting that exponential functions e power 3x and e power 2x? Why we are getting that exponential? Because we are converting that second order or third order or fourth order when the equations, when the roots are different, then that higher order differential equation is going to convert into a first order linear differential equations. That's very important. So that first order linear differential equation, when we solving that, then we get the solution in terms of an exponential function, right? So all of you know, when the roots are different, then the solution is in the form of y1 c1 e power 2x plus c1 e power m1x plus c2 e power m2x when it is a second order differential equation. When the roots are real and equal, suppose real and repeat. Suppose if we are having a differential equation having the roots are 2 and 2, then we are going to take that as a linear differential equation and it is repeating root. Then we are having one arbitrary constant is less. So that's why we are having method to solve that one. So the final solution will be in the c1 plus c1 e power 2x plus c2 x e power 2x. That means c1 plus c2 e power 2x into x. So c1 plus c2 x into e power 2x. So when the roots are repeated. So when the roots are complex, then you are having the solution which is in the form of sin x and cos x, e power alpha x into c1 cos beta x plus c2 sin beta x, right? So these are the different cases when the auxiliary equation, when the auxiliary equation or the characteristic equation having the different roots, right? So we will see one by one. First, we are going to take one by one step method. What are the imports? What are the method? I'll explain each and everything, right? So first we are going to start to solve a homogeneous differential equations. I'm going to take 2 or 3 examples on that one. Then we will shift into the non-homogeneous differential equation. So as all of you know, first we are going to import that one as SymPy. SymPy is a library. All of you know, in the morning session we discussed that symbolic Python import. That symbolic Python as a sim. And we are taking already morning, I can say that whenever we are giving that x as, so that program, that Python program will take that x as a symbol. It is a variable, math variable. It is not just like it is a number. So it is a variable. X is equal to sim dot symbol of x. And here the most important is y is equal to sim dot function of y. What it is represents. Why I am taking sim dot function. Here we are having that one. So if you are if I am using this sim dot function, it represents the derivative of y. This means with respect to x, we are going to, it is a function of y. Y means y of x. Define y as a function of x. Y is a dependent variable and x is an independent variable. That's why we call this as sim dot function of y. So these two are very important because this is the independent variable x and the dependent variable we are always taking as a sim dot function because we are having y of x. Then m is equal to sim dot symbol m. Why this? Because we are going to convert that operator form into a characteristic equation. That's why I'm using one symbol, that symbol as m. So where that symbol we are going to use in terms of in the process of converting that characteristic equation into an algebraic equation, right? So here I'm using some examples, right? Right. So first example, I'm dot sim dot derivative y of x. That means dy by dx. Derivative already morning we saw that one function, right? So sim dot derivative y of x, x comma 2 minus 4 into y of x. What is this expression actually tells? So this is 2 represents the second order derivative, right? So this is sim dot derivative of y of x. It represents. So this is a function y of x. This is x2 means this is the second order derivative with respect to x. This is the way you have to represent. So sim dot derivative of y of x, this is the function. X of 2 means this is d square y by dx square with respect to x. So d square y by dx square with respect to x minus 4 times y of x. So in this actually what is this differential equation represents? D square y by dx square minus 4y, right? So this is equal to the next one is 0. So it is equal to homogeneous differential equation. So this is the way you are going to, this is the example because whenever I am this blue color, so this represents the differential equation like that. Sim dot derivative y of x, x square minus 4 of x. Suppose if I want to express this sim dot derivative of y of x, x square, comma x of 1, it represents dy by dx. So if we are replacing 2 with 3, then we are going to get a d cube y by dx cube. So like that, we can tell that Python programming in this way. Right. Now, so here we are going to define one local variable, that is a sim, because everything we can by run the program, we can learn the program in a simple way. Right. So here already SimPy as defined as a sim. We are going to take that sim as SYM, right? Next, because here I am typing, that's why that. So for the differential equation, first we are going to take the LHS, RHS, because the totally depending upon LHS and RHS of the differential equation. Right. So here we are using some for loop. So in that for loop, we are giving this in this example. So I am taking that label LHS. What is LHS? What is RHS? SimPy expressions. So LHS underscore expression, this is whatever the right hand side, we are going to store it as an LHS underscore expression. The right hand side is sim dot simplify LHS, and the right hand side expression sim dot simplify RHS, right? So we are going to take RHS and LHS. Now this is the method. So sim dot equation. This where it is sim. So that in that SimPy, that sim is there. Sim dot equation. So from that given equation, by using LHS underscore expression and RHS underscore expression, we are taking LHS. We are taking LHS and RHS separately, right? So from that LHS and RHS, we are taking this method sim dot equation. So LHS underscore expression, RHS underscore expression. What is this one? This is mainly our differential equation, right? That differential equation that stored in ODE. So up to now, whatever we are expressing here, that means d square y by dx square minus 4y is equal to 0. Whatever we are entering as an user, that differential equation, that programming, taking it as a differential equation. For that, we return this for loop, right? Again, so first label LHS, RHS in these examples. First, that LHS expression we are converting. So sim dot simplify LHS, the total LHS expression, by using the sim dot simplify method, we convert this total LHS into LHS underscore expression. Then the Python will know that, okay, this is the differential equation. So that is the SimPy expression. That is, then that SimPy will run. Okay, this is the expression which is in SimPy. That is the differential equation, right? So whatever that we are typing, we are converting by using the sim dot simplify. And the same thing, whatever the RHS is there, by using this method sim dot simplify, we convert, that is stored in RHS underscore expression, right? So now this sim dot equation, take that after conversion, take that LHS underscore expression and RHS underscore expression. Now we are ready for differential equation. Where is the differential equation? That differential equation, now it is in ODE. Now our problem is going to start. Now take this ODE and for that everything, whatever we are written so far, for every problem, this is the first procedure. For every problem, this is the first procedure. Again, I am going back up. So again, I am going back up. First, we are going to import SymPy, X as a symbol, and you are taking as Y as sim dot function. It represents Y is depending on Y is a function of X, and we are taking one symbol, right? I am taking one example. This example, I am going to tell the Python, this is the differential equation. How I am going to tell to the Python, this is the differential equation. This is the process. For this process, by using this for loop and by using these methods, I am going to tell that this is the my differential equation. So that differential equation, I am going to store it is in ODE. Up to this ODE, whatever the differential equation you are entering, all the above process is same. Now come to the picture. Now in our hand, we are having differential equation. First, this sim dot expand, that ODE I am taking, that differential equation LHS minus that differential equation RHS, right? So if this differential equation, I am taking the difference of this differential equation, when it is 0 or whatever and whatever, that everything I am going to store by using this method sim dot expand. All these methods are there in that SymPy. I am going to store this one in expression. This is whatever the variable you can choose. I am going to take expression, right? Then next one, y of x. This is very important. What is this yx is equal to y of x? Finally, I am going to take, finally I am going to get the solution in terms of the dependent variable and the independent variable. The derivatives are also depending upon y and x. Whatever the derivatives, everything which is y of x. If we are taking d square y by dx square, it represents y double dash of x, dy by dx as y dash of x, and 0th derivative as y of x. My first motto is to find out the complementary part. How to find out the complementary part in our regular class? Whenever we are having a differential equation, that differential equation, let it be y double dash of x plus 2 into y dash of x plus y of x is equal to 0 when it is homogeneous, is equal to some e power x when it is non-homogeneous. Whether it is homogeneous or non-homogeneous, our first one is to find out the complementary solution. How to get the complementary part? Take the homogeneous part of non-homogeneous equation and convert the left hand side part we are going to write down in an operator form. That operator form, from that operator form, that itself is a characteristic equation, or it is also called an algebraic equation. We are going to find out the roots of that algebraic equation. How you are going to find out the roots? We are going to collect all the coefficients of the derivative. That is the most important part. we are going to collect the coefficients of the derivatives. That coefficients gives us the roots of that characteristic equation. When we are going to solve by using, whenever it is a second order equation, we are having the roots minus b plus r minus square root of b square minus 4ac by 2a. So if that coefficients, we are going to take it as a, b and c. Suppose if it is a second order differential equation. So collect that coefficients. Now this part is nothing but yx is equal to y of x, what it says. Now we are going to collect the coefficients by using that y of x, and those coefficients we are going to store it as an yx. Yx is our user friendly. If you want yx, or if you want any other name, you can put another name, no doubt. Right. Now see, I am going to collect the coefficient of second derivative. See here, a is equal to, now in this expression there is that expression, in that expression what is there? Sim dot expand dot ODE LHS minus ODE RHS. So from this method already we are having that ODE. From that method, from that ODE, that it is stored in expression, right? From that expression I am going to collect the coefficients. How to collect the coefficients? Expression means expr. I am taking this variable. So expression dot coefficient of, where, from where we are getting yx. This is yx, y of x, I am calling it as yx. Previously I noted that y of x, y is the variable which is depending upon x. Previously I defined that function. Yx dot diff of x comma 2. What is this one? Diff of x comma 2 is nothing but the coefficient of second derivative of y with respect to x. Diff of x comma 2 represents the coefficient of derivative of y with respect to x of second order 2. Right. Next one. B is equal to expr dot coefficient of yx dot diff of x. Here you can write down diff of x comma 1 also. There is no problem, but there is no need of write. Diff of x comma 1 you can write, or simply diff of x. Right. So diff of x. I'm maximizing. That view. Yeah, because somebody are asking, please maximize, give 1 minute of time. I am maximizing this one. Sir, is it okay now? Right. So B is the coefficient. That means expr dot coefficient of yx dot diff of x comma 1 we can take. And C is nothing but y of x coefficient, right? Right. Now we got the coefficients of all the derivatives. Now what is the next step? We are going to build characteristic polynomial and find out the roots. How to build the characteristic polynomial? Take the coefficient and solve that polynomial, right? So I'm going to take that am square plus bm plus c. So if you are observing, so Naveen sir raise his hand. Sir, Naveen sir. Naveen sir, any doubt, sir? Because already sir raised his hand. Right. So if you go up a little bit up, so see here. So sim dot expand, everything here we are having. So sim dot expand. So that one we are storing it as expr. So see here the characteristic polynomial sim dot expand. So this is the method. So am square plus bm plus c. Already we know the values of a, b, and c. That is the characteristic polynomial. For this polynomial, we have to find out the roots. How to find out the roots? This is the method sim dot solve. What we are going to solve? We are going to solve this characteristic polynomial char dot poly. Because these are the variables, sir. You can use any variable. Because for this characteristic polynomial, or you can use whatever the variable you want, you can put that variable. So we are going to solve this characteristic polynomial and the roots are m, right? So now, finally, after getting the roots, finally we are going to get the solution of our differential equation. So this is the method sim dot dsolve. So what differential equation we are going to solve? ODE of y of x, right? So that gives us the final solution, right? So this is the ODE. Now we'll see one example. One example, one by one, we will see. Yeah. So these are the, because of how to print that we are going to take that LHS, RHS, and that ODE characteristic polynomial, because we are all using this one, right? So just we are going to print that one, right? So one by one we will see. So here We are taking that one first differential equation is d square y by dx square minus 4y. Already we took the differential equation. What is the characteristic polynomial of the differential equation? M square minus 4. So what are the roots? The roots are minus 2 comma 2, right? So the roots are different. Then we can take what is the general solution when the roots are different? Then c1 e power minus 2x plus c2 e power 2x, right? So now we'll take another example. Again, we'll go to that program. So take another example, d square y by the same dot derivative. I am going to take the d square y by dx square. The repeated examples we are taking d square y by dx square minus 4 into dy by dx minus 2y. Plus 2, not 2y, plus 4y. Yeah, this is the differential equation d square y by dx square minus 4 into dx plus 4y, right? So this is the differential equation, sim dot derivative. How we are going to represent, that is the most important. So y of x, second derivative, and the first derivative is dy by dx, and the 4y, right? Now see the solution for this one, 4y, right? So don't see that one. This is the, because those are the commas. Don't think that it is 4y double dash. Yeah, it is not y double dash. Simply it is 4y, because in that program we have to express in that one the inverted commas, quotes, right? So this is a sim dot derivative if you are observing. So y of x, x square minus 4 into this is y of x plus 4y, y dash of x, 4 into y dash of x. So again that you are using that sim dot derivative y of x, x comma 2 comma minus 4 into y of x comma 1, first derivative, no need. For that first derivative, no need, right? Now go to that, run the program. Again we will see. So we are getting some syntax error. Right, no. So directly we are going to get, right. So this is the differential equation. So what are the roots? Just run the program. By run the program, that is the first example. So I am going to clear all that the previous one, then it is easy. y of x. That is 4y. So by running the program, it is 4y. Yeah. So it is taking only m square minus 4. No, m square minus 4m plus 4. In that differential equation, I forgot that 4y. Please wait. Right. 4y. Right. So this is the way. See, this is the way of expression. Same like that. Sim dot derivative. This is the second order derivative y of x comma 2, and 4 sim dot derivative again y of x comma x. This is the first derivative plus 4y of x. Right. So this is the second order differential equation. Then come down. So if you are run this program, then see the output. See here. So what is the characteristic polynomial? M square minus 4m plus 4. See here. Then what are the roots? The roots are repeated, right? So what is the general solution? C1 plus C2x into e power 2x, right? This is good. So the first example says that different roots. Second example says when the roots are repeated. Now we'll see the complex roots. Suppose we are going to take d square y by dx square plus y. So I am not going to take this minus 4 sim dot derivative of y of x. Simply I am going to take plus y of x. Right. Then I'm running the program. See here. So m square plus 1 is equal to 0. That is the homogeneous equation. So we are having the complex roots. What are the complex roots? Minus I and plus I. What is the general solution? C1 sin x plus C2 cos x. Right. So we are taking that another example also. We are going to take that. See that if that, because here the discriminant is equal to only the real part minus b becomes 0. There is no b term in that one. So we are going to take that b term also, because only ax square plus e we are taking. Then what is the solution we can see? So I am going to take another example like that. B square minus 4ac, and it is some b square, some 25 minus. So I'm going to take some 2 into d square y by dx square. I'm taking one example. Sim dot derivative. 2 into sim dot derivative, because what is this one? 2 into d square y by dx square minus. I'm taking 5 to dy by dx, 5 into first derivative, because I'm trying different examples. Plus simply y, not 4y, just simply y. Now see the solution. Now see here, what is the characteristic equation? Now see the characteristic equation. See, this is 5 by 4 minus square root of 17 by 4. So this is C1 x power, because we are going to get some minus b plus square root of b square minus 4ac by 2a minus b minus. So like that, we are going to find out the characteristic roots for different equations. Right. So, right. So this is the homogeneous solution of a differential equation. Now up to this, we are this is the first part of homogeneous, right? Again, we'll see one by one a brief of the first part of our differential equation. See here. Oh, so only this program is enough when we are solving that complementary solution of different equations. Then people try for different equations and find out the different roots. When it is a homogeneous part, there is no particular integral. Then this complementary solution itself is the general solution, right? So again, I'm going to just I'm giving the brief again. So I'm coming from the first one. So the first one is, first we are going to import that simpy, take the symbol, and y as a function, m as a symbol. So these are the examples I am taking. Examples of different examples, right? So first I'm going to take that sim as sim. This is the local name I'm using. So next one, the next part is, just minute. So, ma'am is asking one question. Sir, please explain, Padma madam, sir, please explain what is local. Right. Ma'am, if you go up, when we say that import SimPy as sim, right? So already that import that SimPy, we are defining as that library as sim. So that always take it as a object, right? So that everything is an object. So sim dot derivative, it takes an object, right? Sim dot derivative. But when it is a local, why we are defining it is a local? It is taking it as string. So sim dot derivative of y of x comma x of 2. Here I am writing, converting string to SimPy expression, right? So that sim object, we are going to convert it as expression. So or otherwise, we get a some error if we are not defining that one, right? So here I am typing. Please, what that actually what it is doing. We can use whatever here. Sim as sim1 or sim2, whatever that one. If we are not representing that as a local, we can get an error, right? Suppose I am giving that one also. How I am going to, if I am not representing it as a local, directly it is taking as a sim. So what error I am going to get? So take local objects in preference. So that converts into an expression. So it converts, it takes an object and that object into expression. So that's why we are using that sim, or otherwise because direct sim is there, one that import SimPy as sim, we are not that SimPy, it takes an object. So everything, if we are taking that an object, then the Python that program cannot understand. We are going to convert that sim as another name. Then it converts into an expression, right? Or otherwise, if you are using that same sim, if you are not using that another variable, then I am going to use that as a funny also. Right, I can get that one. So that is the local variable because sim is the global variable. because that is right. Somebody are asking Sunil sir, why you take y of x as x comma 2, right? Sir, here y of x already we explained when I am coming to the program. See here y, sir. Sir, x is for symbol purpose. Everything that sim dot symbol, already I explained in morning session also. The Python takes that x as a math variable, not it is a number. So that's why first whatever the variable that program, it always takes as a number. So it is not a number, you take it as a variable and it is a math variable. So that's why that x has a sim dot symbol, right? And the next one, y sim dot function of y. What that is main important here, why it is taken as function, because in the derivatives we are always having y is depending upon x. So y is a function of x, dy by dx, d square y by dx square. For that we are going to take that y. That is the relation between y and x. Now come to the point what you are asking, Sunil sir. So here I am taking sim dot derivative y of x comma x comma 2. Sir, it represents that derivative. Sim dot derivative is a method. That method is in that library SimPy. So because already we are taking that SimPy as a sim, from that library there is a derivative method. We are taking that derivative method. I am calling that method as a sim dot derivative. This derivative is already there in that SimPy. So I am taking that sim dot derivative. This y of x, already what is this y of x? Already we defined a function y. That y is with respect to x function, comma x comma 2 derivative means d square y by dx square. That means the differentiation of y with respect to x 2 times that it represents. So again I am taking here sim dot derivative of y of x comma x. What it represents? Sim dot derivative y of x comma x means y of x comma, here we can write down x comma 1 also. Here I am writing, if you are having any doubt, here again I am putting the brackets here, y of x comma 1. That's it. That's it. So what it represents? So it is the derivative of y with respect to x 1 time. Plus, no need of that 0th derivative, we can simply take it as y. Sir, are you got the answer, sir? Sunil, sir? Padma madam, is it clear for you? Yeah, right. So, this is the, yeah, thank you, ma'am. Right. So, this is the first one. And then again, that already we defined that local. So, up to this part, sir, up to ODE, for any problem, this is the common structure. And then, so this is our main program. First one is find out the characteristic equation. We are going to extract all the coefficients. Next one, build the characteristic polynomial. First extract the coefficients and build the characteristic polynomial, and finally find out the solution. This is because for this all these prints are in that output, what is there, we are going to express that as just print, right? Okay, then next we come to the second part. Suppose when that differential equation, here you are here, if you are observing, sim dot is equal to 0, right? So where in that place, if we are having forcing function, then that forcing function, whenever the forcing function, we are getting the complementary part as well as the particular part. The particular part depending upon the forcing function. So first, as usual, we are going to find out the complementary solution, and then we are going to find out the particular solution, right? So this is the example I am taking. Sim dot derivative of y of x comma 2, what it represents d square y by dx square minus 4y. So here, just this is the right hand side part. Just I am taking only e power minus 2x. I am not going to take that the remaining one. So I am going to cancel that one. I will see one by one. Right. Sir, here, what is this differential equation, sir? D square y by dx square minus 4y is equal to e power minus 2x. Already in the morning, I explained whenever we are having the trigonometric functions, logarithmic functions, exponential functions, then we have to express in this form sim dot exponential dot of minus 2 star x, right? Now this is my differential equation, sir. D square y by dx square minus 4y is equal to e power 2x. Now we are going to find out the solution. This solution having two parts. One is the complementary part, another one is the particular part. So first we are going to check the complementary part and then particular part, right? Now the same thing, whatever the program, that program works out for every example, right? Now see, what is the input? Input is y of x comma 2 minus 4 into y of x. What is the RHS? RHS is e power minus 2x. What is the differential equation, sir? Derivative d square y by dx square minus 4y. What is the characteristic polynomial? M square minus 4. Naturally polynomial which is equal to 0, sir. What are the roots? Minus 2 comma 2. Then the first part is the general. It is not the general solution because we are going to add that second part also. We can get the general solution, but I am not writing this general solution, right? Just this is YC complementary solution, right? What is the complementary solution, sir? So that is the complementary solution. C1 e power minus 2x. This is the final general solution I got directly. So first I am going to find out the complementary solution first separately, and then find out the particular integral separately, and then we can combine these two, we get the solution. Right. So here we are using one method. That method is called here C. Solution is equal to sim dot dsolve. This is a powerful method of dsolve solution. So this is the method in that sim. So we are going to get that dsolve. By using that one, we can get direct solution. If you want separate the particular solution also, we can do the separate program. But that is the most important. Not I am not advisable to solve directly using dsolve, because when we are using that dsolve method directly, we get the solution. But we must know, like in that characteristic polynomial and that complementary solution, like that, we are going to find out the particular solution separately. Then by combining those two only, we get the solution. But what this dsolve is doing, that dsolve Whenever we are using this method, we can get the direct solution. So whatever the solution, you are going to get that desolve ODE of y of x. And by using this method desolve, no need of that characteristic equation, characteristic polynomial, whatever that directly enter the differential equation. By using this method, we get the solution. But that is not the correct. Just a minute, I am going to use that like that complementary solution. We are going to separately how to find out the particular integral for a given differential equation. Just a minute, wait for 1 minute. Just 1 minute, sir, because I'm trying that particular integral program separately. I'm not using that desolve method, because by using that desolve method straight away the student get the answer just by entering the differential equation, and that sim dot desolve gives us the direct solution. That is not the correct way to solve the differential equation. So the correct method is first find out the complementary solution. Whatever we did, that is fine for finding the complementary solution. Like that, whatever the classroom explanation, whatever we are doing, the same way we are going to do for that particular integral also. Because if we know one problem, then we get for every problem. Okay, so this is the characteristic polynomial. First root sim dot solve. We are getting the complementary solution. Now find out the particular solution. So we'll see that one. We take the differential equation. That one only first, only the particular integral part we are going to observe, right? What is the right hand side function there we are taking? So sir, sir, please tell me, sir. Vijender, sir. Sir, please type your message. So I can take that program is somewhat. Okay, we can use that D-solve up to now and so this is the general solution. This is printf, right? So particular integral. So this is a somewhat a typical program, right? To find out the particular integral. So we have to learn all these loops, or otherwise we can get a simple program. But here we are going to take all the steps. So just run the program for that one example for simplicity purpose. So take one example. So homogeneous case and no forcing function. So homogeneous case and no forcing function. So we are using if else. Suppose that means again we are going to take that one, the RHS is equal to 0 or not. If RHSX is equal to 0, then it is a homogeneous function. If RHS not equal to 0, then again we are going to take the integration, and we are going to take the left hand side part to the right hand side part, and we are going to apply the methods, and we are going to take the suitable particular integral function. So all these are in that program. So if we are going to do this all these things, then it is better, or otherwise we are going to use that desolve method. But we have to, in that lab, we are going to use this only. So this is one. So by example, I'll give. So I am giving one example.
We have only 1 year to from now. Yes, one, P1 part. Yes, one. అంతే కదా ఏదైనా ప్రాబ్లమ్ మల్టీ వేస్ ఉంటాయి సో అలాంటి కోడ్ మల్టీ వర్క్స్ ప్రతి లాజిక్ అడ్వాంటేజ్ డిజైన్ ఉంటుంది brute force అంటే ఏ పరివర్తన కాకుండా నేను చాలా బెస్ట్గా ఉండొచ్చు
Variable separable method. We're always using the variable separable method, right? Straight away, I'm taking one example. So this is d square y by dx square minus 4x, and the right hand side function is so this is the first one is the complementary solution, and the final particular solution is that minus x e power minus 2x by 4. The complementary solution and the particular solution. So this is the final general solution of that equation. For this particular solution, we are going to use that program separately, and that program always depending upon the variable separable method. But the variable separable method we are using for up to a second order differential equation. But if we go higher order differential equation, dqy by dx, then it is somewhat complicated, that program. So basically we are going to do that variable separable method up to the second order differential equation. This is the program, and we can get this program by using that online also. We can directly this program we can get. So here we have to run the program, right? So this is we are going to take y1 and y2. You know how to find out and y1 and y2. Here we are using that in a method of variables, where variables method of variables. How we are going to get from that homogeneous part, we are going to get the two solutions. So two solutions, we call it as y1 and y2. So that y1 and y2 we call it as, and take that Wronskian, you know that we call it as w, we call it as that Wronskian, and that y1 of t is we are going to integrate that one here. So you know that one, that right hand side is the forcing function r of x. Then what is the formula for u1 of x, a of x and b of x? So that means minus y2 of x into r of x by Wronskian of y1 of x comma y2 of x, and that b of x is nothing but y1 of x into r of x by Wronskian of y1 of x by 2 of x. Mainly we are using that method to find out that particular integral, right? So that's why we are finding that y1 and y2 and find out that Wronskian. These are all the steps, and this is integration I1 and I2. So finally we got that expression, right? Then finally we got the general solution. The general solution is the combination of that complementary function and the particular integral. So we'll take another example.
Which language there is no equation are also second space comes.
So that means I am taking that right hand side function. That means that sim dot derivative y of x comma 2 minus. Here I am taking a sim dot derivative 4 into. Yeah. So sim dot derivative of y of x comma 1 minus 2y that is some tan x, not e power minus 2x, it is tan x. So then we can solve this one. So the general solution and the particular solution. Right. So again we come to that slides. So we are having here that these are the programs already there in that Cauchy linear equation, but we don't want all those programs. Only Cauchy linear equation, Legendre type linear equation. So we are not going to use that one here up to only that 4 method of variation of parameters. Up to that one we are having, and the forcing functions are exponential, sin x and cos x, a polynomial function. The same thing, whatever the function we are going to give in that program, and by using that second part as a particular integral, but it is very somewhat complicated when it is a third order differential equation. But I'll also try for that third order differential equation, but in that program we are using only by using a method of variation of parameters. From that only we are getting y1 of x and y2 of x Wronskian and take the integration. But when we are going to the higher order, then program is somewhat complicated, and this is all of that second order differential equation, right? And I'll share that whatever the programs of first order and second order differential equation separately, and I'll share that I'll prepare one lab manual also. So within a week time, I'm going to send that lab manual to Dr. Srinivasan sir. So sir can share to that lab manual to all of you. Right, I prepared each and every program, and for that, on that program I prepared some examples and everything. So I'll send that one. So that's also today's program. Sir, Srinivasan sir.
Sir, starting meeting, sir. Thank you very much, sir.
Okay.
The session on first
sir, any clarification, any doubts? Sunil sir, actually, any questions can you ask Sunil sir? Yes, exactly what you said is correct. This program is lengthy, and students definitely feel difficult, sir. That's why I'm going to cut all these programs into a simple programs, sir. So that's why I'm going to prepare that one. My planning is whenever the student, I'm going to prepare that lab manual. I already prepared, but somewhat lengthy programs. So within a week of time, I'm going to prepare that lab manual. That lab manual is how the students are going to do and what the SARs are going to present in that particular lab. Suppose when we are having a first order differential equation, suppose the student enters the first order differential equation, then the first lab session is variable separable method. If it is not variable separable, homogeneous. If it is not exact, inexact, different cases. Like that I'm preparing, sir. So what you said is exactly correct. It is very difficult to understand that long program. So I'll send that lab manual very shortly, sir. Then anyone?
Lower, sir.
Yeah.
Thank you, sir. Srinivasan sir is not available right now. He's in meeting.
Right.
Thank you very much, sir. The session is very explained clearly, and you excellent examples. The session was engaging, informative, and useful for understanding both theoretical and computational aspects. This topic will greatly help the participant in their academic and research activities. Thank you for the excellent session, sir. Thank you very much, sir.
Thank you, sir.
And the next session will start on tomorrow, sharply 10 a.m., sir.
Thank you, sir.
Yes, thank you, sir.
Thank you, sir. Thank you.